I don't really have an outline here because I'm going to jump around a little bit, so let me just sort of warn you about some of the stuff that's coming, right? I'm going to talk about self-driving cars, sort of how they work. I'm going to talk a little bit about the societal impacts, what this is going to look like when we have self-driving cars everywhere. I'm going to talk a little bit about the machine learning that's behind them, how they work. And then having talked about the machine learning, the AI, I'm also going to show you a couple of other things that it's used for, and also talk about that software development process, like how do we develop these systems that are primarily machine learning based. So I'm going to jump around a bit. There's even some videos of robot snakes toward the end, so bunch of random stuff. So let me get started. And I'm going to start just a little bit with history because you're all here in Pittsburgh, and in case you're not aware of this, it's not an accident that Uber came here to start its self-driving car effort, and Argo and Aurora and Aptiv and all the other efforts here in Pittsburgh, because much of this started right here at Carnegie Mellon, going all the way back to the 80s. These cars were being tested on campus. This car here in '95 drove from Pittsburgh to LA over 98% of the way with no hands on the wheel. That's where the name No Hands Across America came from. For those of you that remember Hands Across America, this was No Hands Across America at the same time. There's also in the sort of the big, well, there may be two watershed moments. The first of those was the Darpa Urban Challenge in 2007, right? Darpa sponsored this contest. And we went out in the desert into this mock city and showed that we could drive cars around. And that's when Google started its self-driving car program. So that's when people sort of realized this was going to work. And of course, scrolling ahead more recently, the second watershed moment, this was in 2015 when Uber opened its self-driving car effort here in Pittsburgh. Many of the faces, my involvement in self-driving cars really started around this time. Many of the other faces you see here were the people that built some of those previous systems there. And of course, this was the second watershed moment because when Google started their effort back in 2007, 2008, it was just for fun. When Uber did this, although there were lots of efforts underway at many companies, this for all those companies was the oh crap, someone's actually going to try to do this moment where they all had to get serious, right? And so that's where you saw the explosion. Okay, so let me jump in. Some of the motivations for doing this, I think many of us are familiar with us now, that after years of declines, most recently the number of deaths has gone up in the last few years. It's on the order of 40,000 a year in the US. What that means is just in the hour and a half time that this session's scheduled, 6 more people will die in the US. It's a little scary when you think about it that way. If you want the global numbers, you can just multiply these all by about 30. And so that's what happens around the world. By the way, there's a couple more chairs up here. If you guys want to sit down here, feel free to just come up here. You can have mine. I won't be using it. So, of course, the government, we're not the only ones to realize this. The government realized this and said, oh, well, okay, let's figure out what's going on. Why are all these people dying? The print's a little small, but what this first chart says is we found the problem sitting in the driver's seat. 94% of these are attributable to mistakes made by the driver. And so then they dug in one step deeper and said, well, okay, what did the driver do wrong? And so the biggest category is what's politely referred to as recognition error. And what that means is basically you weren't paying attention. You were thinking about how stressful your day at work was, or the errands you have to go run, or making plans with your friends, or you just didn't see something that you needed to see in order to drive safely. The second biggest category is also politely called decision error. What decision error means is you were driving too fast for the conditions, you did something illegal, or you just kind of didn't understand what was going on around you and did something stupid. And so those are the big categories. And so what does a self-driving car do about that? So this is Uber's self-driving car. And the first thing to deal with the The recognition problem, right, it's full of sensors. So starting on the very top is a LiDAR sensor, which gives you 360-degree coverage. What is LiDAR good for? It gives you very precise 3D location of every single point that it captures. So that's what you get from LiDAR. Right underneath that is a 360-degree ring of cameras. So what do the cameras give you? You get higher resolution, and you also get the 3 color channels, right? So it's much better for recognizing what you're looking at. And then you don't see it on the outside, but there's 360-degree radar coverage. And what does this give you? This is a direct measurement of the velocities of the object you see. So when you put all these things together, you have everything you need to figure out what you're looking at, where it is, and how fast it's moving. So all of these solve the recognition problem. And of course, the important thing about these is they never get stressed about how rough their day was, and they're not texting their friends while they're doing this either, right? All the time they're on. So now the decision-making part of the problem, and really that's the part we're here to talk about today. That all happens in the trunk. You can't see this, but there's a custom compute board here. It's full of CPUs and GPUs, and so this is where all the decision-making goes, to turn all those sensors plus some GPS, IMU wheel encoders into controls on the actuators. And so that's mostly what I'm going to talk about. Before I do that, I think it's fun just to put up what would be a boring video in any other context, right? We see this all the time. Until you put yourself in the shoes of the person who's going to type in the code to sort all this out, right? This is complete chaos, right? You're driving around, there's all these different types of actors. They're going all different directions for inexplicable reasons. There's all these crazy lights and signs and things flashing at you. There's things that say stop, and you need to pay attention to those. There's other things that say like stop smoking, and we should pay attention to those, but the car doesn't need to read that one, right? So there's all these confusing things. Of course, the people who design these roads try to help, right? They draw these nice lines and things on the road so you can figure out what things are and where they're going. And of course, helpfully, half the actors just ignore those lines and go wherever they want anyway. So as an AI problem, the thing you realize right away is nobody's going to sit down and type the code in that does this, right? We are going to use machine learning extensively throughout this system. It's basically the only way it's possible. And so what I'm going to do now is I'm just going to switch over to machine learning. And it's much talked about, but I want to just put a mental note in your head what to think about, because people say machine learning and it gets to sound kind of mystic after you hear enough journalist sort of descriptions of it. And so the first thing is most of what is commercially successful so far is what's called supervised learning. Okay, and what does supervised learning mean? So let's just look at a really trivial example, just to give you a mental note to put in your head if you're not more familiar with this. Say you're running an ice cream shop on a beach. You said, wow, I can't figure out how much ice cream to bring with me in the morning. This machine learning is really good. Maybe I can use machine learning to figure out how much ice cream to show up with every morning. So sure, you can use supervised learning. What do? You go, and every day you write down what the temperature was that day, and then you record how many ice cream cones you sold. And you get all these data points for the different days. And so that's the data you would collect. And there's an important thing. So how many ice cream cones did I sell? This is what we call the label. This is the kind of thing, this is what we want to predict. And the reason I bring this up, as I'm talking in the future when I talk about the labels for data, this is very important because people will come all the time and say, oh, I've got so much data, you wouldn't believe how many terabytes of data are sitting on my servers. I am so ready for AI. You don't have any data until you've got labels of something you want to predict. And so it's good to keep that in mind, right? Okay, so what do then? You learn a model for this. In this case, model sounds fancy. You can just draw a line, but what are you going to use for this model? What you're going to do is now in the future you can make predictions with this, right? When you show up at the beginning of the day, you're going to say, oh, here's the temperature. You're going to look at your model, and you're going to say, okay, this is how much ice cream I need to bring today for my ice cream cones. Now, those of you who are more familiar with this, if you remember from high school, this model, a line, only has 2 parameters, right? And if you remember your calculus, you'll know that you can actually solve for what those 2 parameters should be to minimize the error between all these points in a nice closed form solution. Very, very easy. But this is machine learning. This is all it is. You collect some data and fit a model to it. Now what happens is, and so if anything else I say about machine learning confuses you, just map it back onto this picture. Some inputs, some labels, some data, I fit a model. Okay, so it's easy if it's a straight line. Of course, things don't go so well if it's not a straight line. And of course, the other big thing happens is that you don't just have one x-axis, one y-axis, right? You have hundreds of inputs, thousands, millions, maybe the same on the output, right? Okay, so what happens? So here's just to give you a step in that direction, right? What if the data was actually this? Right now the model's got to get more complicated. So this particular model now has 3 parameters, and worse yet, there's no closed form solution. You can't just write down an equation for what those 3 parameters should be. And so what you do is you do something called gradient descent, where you just basically try to tweak those parameters until you find ones that fit better. And so what happens is you keep building from there. Okay, so this is nonlinear, 3 parameters, still 1 input, 1 output. But what we really want something, if this model wasn't right, it won't fit this correctly, maybe you can't do gradient descent. Really want something that's got so many parameters that basically it can fit anything. And you don't even have to know the form of the function, it's just going to fit it. Okay, so this is where deep learning comes in, right? So what deep learning does is takes the inputs and through a series of functions like the one I showed you there, it just stacks them up on each other. You get the inputs at the beginning, the output of that function is combined with other functions, and you stack it up to another layer, so those outputs become the input to the next layer, another layer, those outputs become the inputs to the next layer. And you literally do this to the point where you've got millions of parameters. So it gets a little bit crazy. But you can use gradient descent still to try to look for good values for those millions of parameters. Those of you that have a statistical background will realize, or maybe this will be obvious to you even if you don't have a statistical background. If you think back to fitting that line, the line has 2 parameters to it. What if you only gave it 1 data point and said, okay, learn a model? Right, it's not going to work, right? There's an infinite number of lines that could go through that 1 data point. You're not going to learn anything, right? So now I've just told you this thing has millions of parameters in it. How am I going to get anything sensible out of this? Well, the answer is obvious. You need millions of data points, or you are not going to get anything sensible out of it, right? And so the big input, the big insight from 2012 was that if you have lots of data, meaning millions, and you have lots of cycles, basically meaning GPUs, you can, and some careful algorithms, you can actually do this. This actually works. And this is why, since 2012, deep learning has had a large number of successes in large-scale machine learning problems, and especially images. Okay, so now you've got just a mental note for yourself about when I say supervised learning, what to think about. Now I'm going to jump back over to something closer to what we would really care about with cars, right? So what would we like to do with cars? Well, we would like to use supervised learning to recognize, say, pedestrians in the road. Okay, so what does that mean? Easy to collect lots of video, right? But if you have no labels, you have no data. So the next thing you do is you pay people to look at these images one at a time and draw boxes around all the pedestrians they see in the scene, all the other things they see as well that are important. And so what you do is you will take all these labels and chop them out. So you make each of these, so these each become one data point now. So here's a bunch of image pixels, and there's the label. This is a vehicle. Most things are nothing, and that becomes your training data. You need millions of those if you're going to train one of these models. And so then what do? This is just exactly the same picture I just showed you before. Those raw pixels are going to be fed into this network, and they're going to try to predict. You do just like a one-hot encoding of the labels there. You just have one output for each class you're interested in, and you just mark 0 or 1 whether it's in that class. So you train this with your GPUs. Now when you go to use this, you do something a little bit ridiculous, but this is essentially what you do. You get a big image like this, but you still don't know like the size, the shape, the location of all the objects you're looking for. So what do? The most naive thing you could do. You just chop it up. All sizes, all shapes, everywhere in the image. You just make a ton of them, and you put each of them one at a time through your network and say, is this the truck? Is this a truck? Is this a truck? Through all of them. And you get all those predictions. And if all goes well, you end up with a video that looks like this. So this is now the deep learning network. And of course, we've all seen many of these now. But this is what you end up with. So this now recognizes these objects, and of course you have other ones to recognize other objects there. Okay, so that's supervised learning. I said this is used pervasively through the autonomy system. Let me now show you what that looks like. What is the system architecture for a self-driving car? And again, this is pretty much all the major efforts are using exactly this architecture. There are a few small companies doing crazy things, but this is basically it. So this is what it looks like. So what's our problem? We've got all these sensors over here piping in all these images and everything else, and somehow magic has to happen, and we need to get down there where the actuators are and make decisions for the accelerator, the brakes, the steering, and the signals. So how does that work? So I'm going to step you through these boxes one at a time and show you what I mean. So the first thing that happens is maps and localization. So cars out there in the world, first question it has to answer is, where am I? And so the way that works is, these cars aren't going to drive anywhere they haven't already mapped in great detail. So when I say mapped, I don't mean like what's on your Google phone where you say, hey, what's the direction to the coffee store, right? It's a full 3D reconstruction of the entire environment around. And so what happens is, it's not drawn here. This is where the car is sitting. These are all the LiDAR sweeps around it. What it's doing is taking this 3D scene it's just observed and physically matching it to the 3D reconstruction in its maps so it can figure out precisely where it is on the road. And so what this means is, it uses GPS, but even if the GPS isn't there or isn't perfect, which often happens, it can still localize itself to a very high precision using these maps. Okay. So now I figured out where I am. Next question, who's out here with me? So that is the perception system. Okay, now the perception system is going to heavily use what I just showed you with supervised learning, right? It's got deep learning models to recognize all the objects we're interested in seeing on the road. And so here's a video that gives an idea what this is like. So this is our car in the middle in this wire frame. This is all being detected on board the car in real time. So all these boxes are other vehicles on the road. These yellow circles, this isn't noise. These are pedestrians. This really is a herd of them coming across in front of us. And I don't know how well you can see, if you look at the top, it shows the video of it's a bar scene at night, right? So there really are that many pedestrians out here on the road. Okay, so these are all the things that have to be detected. And you'll see these little arrows that come out. That's the current estimate of their velocity vector. Okay, great. So now we know who else is out here with us. Next question is, what are they going to do? And so we've got a velocity vector, but we really need more than that if we're going to make a good plan for ourselves. And so this is called the prediction problem. And so what you'll see, this is another view. Here's our car. These are the other ones. And you'll see they have lines coming out of. These lines are their predictions about where we think we're going to go. And you see they're multimodal. So there was a prediction for this car to go this way and go straight, or that way and take a right into that shopping center there. So we have to predict all of the possibilities that this thing might do. Here's the bar scene again. And you'll see, importantly, here's all these pedestrians, and you'll see all these lines going across these crosswalks in this direction and not in this direction. And that's really, really important, right? If you get that wrong, and we're trying to go through this intersection, and we get tons of predictions going crossways in front of us, we're just going to sit there and do nothing. And it's going to look really stupid, right? People are going to be honking at us, and even the rider is not going to be happy because we're not getting anywhere. Of course, if you get it wrong the opposite way, it's even worse, right? If all the pedestrians are coming across and you said, nope, clear sailing, that is not going to go well. And so these are really difficult, but you can see it does a pretty good job of getting these right. When this goes around, I wonder if I can. It's always a mystery whether the pause will work on these things, but I'm gonna try this when this loops one more time, because okay. Let's see if this. There is. What I want to point out is this is a bicycle here. This bicycle's come from this parking lot. And it's actually wandering a little bit. So it kind of wanders that way. Very briefly, it looks like it's going across this way, but then it actually kind of swerves and goes this way. And so we get that right. We very briefly think there's one here, but even before he's left the sidewalk, we correctly say he's going to go this way. So I don't know if what's going to happen when I push this again. Let's see if this actually goes, yeah. So you'll see there's kind of there's a little blink in that direction, but before long it says all the way across, and he's still on the sidewalk at that point. So that's the level of subtlety that we have to get these predictions right, or bad things will happen. Okay. Next thing is the motion planning. Okay, so we've understood everything about the world around us. We know where we want to go. That comes from the Uber app. And we have an idea where everybody else is and where they're going, and we need to make our own plan. How are we going to proceed? And so here's just an example of this. We're going to make a lane change, but there's someone behind us in the lane, and there's someone changing in front of us in the lane, so we need to find that spot that's between those two. The way that works is there's a cost-based optimization. So what we do is look at sample trajectories, and there's a cost for getting too close to the other objects, and so we find the optimal path that has the minimum cost for that to happen. I realized now when I was talking about the prediction problem, I forgot one really cool thing about it, which is it's done with supervised learning, right? Just like recognizing things, the where are people going, that's done with supervised learning. The cool thing about that is it's easy to get the labels, right? Because all you do is you take that video you collected, which was easy, you run that perception system to detect all the objects on it, and now what you do is for every snapshot of that video, you say, here's the current state of the world, and what are my labels? I'm trying to predict where these things are going to be in the future. I just scroll the log ahead, however far I want to predict, 5 seconds, 10 seconds, and there's the answer. That's where they are. That's what the prediction should be. So it's really cool. You get a ton of, that's one of the nice instances where that we have lots of data, and yes, we actually have lots of data because it's easy to get more labels. Okay, so coming back to this, we put all of this together, and we have a system. And so this is actually a very old one, but I'm just going to put this up. because it shows a couple of the other elements that I didn't have a chance to describe yet. So here we are in the gray, and we've got these other objects around. What you'll see is there's all these lines on the roads with arrows on them and things. So those come from the map. Once we know where we are, we've already pre-recorded exactly where all the lanes are, which direction they go, and which other lanes they're connected to. So we don't have to figure that out on the fly from trying to look at confusing Pittsburgh road markings and geometries. It's all written down for us in advance because we know where we are. Same thing with the traffic light up there. We obviously have to detect what color it is in real time, but we already know where it is. So we know exactly where to look for it, and we already know, again, thanks to confusing Pittsburgh signs and things, we've already had someone offline write down exactly which lanes does that green light pertain to. So we don't have to figure it out in real time. We're just reading that out of the map. Okay. Let me jump to something different now. So let's see. I should have timed myself. This is a super oversimplified view of our architecture, obviously. The diagrams that we really look at when we try to understand the system have about 100 boxes on them, right? It's really complicated, and even this simple one took me, many minutes to describe to you. And so the obvious question is, I told you just before this about deep learning and how we can take millions of data points and millions of parameters and do magic. Why can't we just do that? Let's get rid of all that code. It's confusing anyway, and you have to debug it, and let's just use deep learning for the whole problem. It turns out, yes, you can do that too. So this is called imitation learning. And again, it's supervised learning, just like all the others. The way imitation learning works is that you tell your drivers, just go out with the cars, turn the sensors on, so you're collecting all the sensor data, and just drive around. Just drive the way you would drive. And so now you have your labeled training data, right? You go back to those logs, and in the logs you have, when I saw this input in my sensors, here's what a real driver did on the car. So when I see this, that's what my self-driving car should do. And you just collect a ton of that data, and you train the deep network to do the same thing. Now, there are a bunch of tricks with this to make this stable. By itself, it's not perfectly stable. The problem with human drivers is they drive down the middles of lanes and things. And so when you train your algorithm, you get good performance right in the middle of the lane, but just due to the noise in your model and any other kind of noise, at some point your car will drift a little bit outside of that. And all of a sudden you find yourself in a place that's not bad, you're okay, but you don't have any data from the human driver because they never did it. So you don't know how to recover from that. And so you do something kind of random, and then you're even farther from where you're supposed to be, and you have even less data. And what actually happens, we did this, if you train it just completely naively, your car will seem like it's driving pretty well and will just drift right off the road like it didn't see the lines for this reason. But what you can do is augment the data to cover that up. So you basically, you slide the data around to give it examples that are a little bit more outside the data you have, and that makes everything stable. Okay, I'm gonna skip the pictures of how you did that. And this, what this says is yep, sure, yep.
Quick question, what happens when construction happens on your known route?
Yeah, so this is a problem for, it's a different problem for these two different systems. The first one I saw you with the whole decomposed one, mostly what happens is we recognize that, hey, the map doesn't match, the world doesn't match the map we're in. Let's pull over and basically call for help. Now what's incrementally being worked on is, okay, it's construction, but if it's kind of obvious, we can figure it out on the fly, that there's a clear lane, everybody's following it, we'll follow it. And so we're in the process of sort of ramping up that skill level. For this approach, Basically, the idea is going to be roughly the same, but we're going to have to show it examples of construction. This system's not so rigid, so often it makes it through the construction anyway. But I'll get to, at the end of this, I'll get to a couple more comments about the trade-offs between these two systems, but yeah. Okay, so this actually works. So here's one of our cars. The way you know this is self-driving is this little green check right here. It's coming up to the Fort Pitt tunnels. Those of you that flew in from the airport, this is the path in from the airport. It's fine. It goes through merges, gets down to the tunnel. Everything works well, and it's cool, right? Because this thing has virtually no code on it, right? The only software on this thing is the thing running the sensors and copying their data onto the front of the neural network, and then copying the data from the end of the neural network back onto the actuators. And that's the only software there. It all runs on a GPU. The neural net runs on it, sorry. The neural net runs on the GPU. The sensors are still controlled by CPU, but most of that big compute board is sitting there idle here. And this all runs fine all the way to the tunnels. You can do other fun things. So this one's kind of fun. Don't worry about the speed. This one's a replay from a log, right? It's replayed at 3x real time. But it is a highway. It is highway speeds. And the cool thing about it is all these raindrops. So this actually is the image it's driving from. And so we did verify one thing. If you train it without any data in the rain, it doesn't go well. but if you train it, if you have your drivers drive around in the rain when there's this kind of stuff on your camera lens, it'll learn how to handle that just fine. Okay, so arguably, the what of what's demonstrated here, just stay in your lane and follow the car in front of you. It's easy. That's actually what those systems back in the 90s were doing. It's what your Tesla does already. It's not the hardest problem. And so people have argued, okay, you did this imitation learning, but you can't learn anything very complicated with it. You can just learn these really super basic things. That's not quite true either. So this one is for fun. This is one of our early attempts at a stop sign. And what's funny about this one is we don't even have enough data to stabilize the steering yet. You can see the steering's kind of jittering all over the place. But nonetheless, we're following this car up to the stop sign. We get to the stop sign. We stop for this car to come across. There's a truck over here that cuts in front of us. And okay, so now it's our turn, we go. So again, I said now it's our turn, we go. That first system with all the boxes actually does that reasoning, right? It's tracked every single vehicle. When did they arrive at the stop sign? Whose turn is it now? This one didn't do any of that. There's no logic there. It's just a big network, right? And so it turns out this really is imitation learning, right? Because the video was so jittery you couldn't really tell, but it didn't stop at the stop sign. It did what humans do. It sort of slowed down a lot and then sort of crawled forward looking for an opening, and as soon as it saw one, it went for it. And so this really this is sort of truly imitation learning. Now, getting a little bit back to the comments I made before, so what did Uber ultimately decide to do? What they ultimately decided to do was not use this imitation learning approach and invest all the resources in that first method, that sort of decomposed into lots of boxes approach. And the reason is because this method is a black box. When it does something that you don't understand or was wrong, it's hard to figure out why. We built some really cool tools to sort of help debug these kind of systems. But it's just not the same as here's a bunch of code. I can tell you which module gave the wrong output. I can go in line by line. I can find the mistake, right? And so because of that, Uber ultimately abandoned this approach and went with the first approach. Okay, I am going to switch and just talk to you a little bit about our software development process. So it might be a good moment for me to pause for just a second if there's anyone that wanted to ask a question just about kind of the architecture here of how the, yeah. And the, yeah, okay.
Really interested in the boundary area between the motion planning and vehicle control.
Yes.
I'm interested in your views on how much information you think motion planning needs about vehicle capabilities, what the vehicle can do, how it can do it stably, and also where the line is for things like safety features like collision mitigation. Is that more the and maybe it's everything, but is it more the responsibility of motion planning, or is that something that motion planning kind of is going to let the vehicle controls take care of when you get to that point where now you've lost traction, now you're going to hit something,
Yeah.
you did make a mistake, take over.
Yeah, so the motion planner has a model of the vehicle dynamics. So it knows what the vehicle can do, and it uses that model in its generation of trajectories. So it's able to understand things at that level. It should not be giving the controllers something that really they just can't do. So that's that side of it. You asked about collision mitigation. It is the job of the motion planner to do the collision mitigation. It needs to understand the scene and the cost function and the penalties for various things, and A, avoid collisions, but B, mitigate the effects if they're inevitable. So that is the job of the planner. Now, in reality, what you do is you have this system running, but if your car has its own completely independent collision mitigation system, you should set it up so that's running as well, completely as an independent process that can just take over and do its things if it needs to.
Do you think the latencies are sufficiently small so that motion planning can do what it's supposed to do for that?
That's part of the challenge, is getting the latency end to end of the whole system down. I can't comment on the latency of this system because it's not public, but that is one of the challenges, is to work on that latency. Yeah.
I have a question about the imitation learning, and you mentioned that it's a black box, and you also mentioned that you have some cool tools to debug the black box. So I'm really interested in that. I mean, it has been said for decades that neural networks are black boxes. But is there any way now that we are developing like forensic tools to figure out what went wrong in the neural network and how we can sort of nudge it a little bit and stuff like that?
Yeah, so I can give you an example of one of those tools, and then you can tell me whether you think this is makes it less a black box or not. So one of the tools is, if we take the car out and it just does something wrong. It's cruising along and it swerves onto the shoulder. What we'll do is go back to that log, find those frames where it took that action that it should not have taken. What we do is take those inputs, we put them back into the front of the network, the input of the network. We propagate them through, and so at the end, the outputs of this thing, we've never seen this before. It's not supposed to do that, right? So what we do instead is we take the middle layers, the activation levels of the middle layers of the network, and then we go back through and do the same thing with all of our training data and find those training data instances that create the same internal representation. And then we go back and ask ourselves, usually what we find at that point is training data that's got something wrong with it. Either the driver actually did something stupid in that particular training data, or we collected the training data for some place we didn't mean to collect it, right? We were often, who knows what, we were in the garage or something when we're not just training the thing to drive in the garage, and suddenly we've got this in our data, things like that. So that's one kind of debugging. And so often what you would do then is basically you just take that data out of your training set and you retrain things. So that's one example. I can see by your face the answer to your question of does that make it less of a black box or not. But that's one example of the kinds of things we do to try to make it more understandable or more debuggable. Okay. All right, so I'm going to jump forward here. So how does this development process work? Of course, you know, this is a tech operation, right? This is broadly speaking an agile development process, and so how do we go through this? And so in this case, what happens is we have all these logs for how our cars drive. So right when we're testing the cars, what are we doing? They're out on the road, they're driving in autonomous mode, but there's a safety driver there who just takes over when something goes wrong. And so all those events are logged. So we go back there and find all the places the driver had to take over. And we do essentially what would be a classical data mining problem, right? We pull all those events out, and then we start trying to cluster them and say, well, where are the locations where things went wrong? What are the scenarios where things went wrong? What times of day? What kinds of weather conditions? And you find these big clusters, like what's my biggest problem right now? And those will be handed off to engineers and say, okay, here's a bunch of examples. You're going to figure out why these things are broken and fix the code. So that happens. They will make some changes to the code, and then what we're going to do is we'll have the ability to replay. So they've changed the code, right? They've got their diff up. Hey, I think this fixes our problems. What they do is they'll replay a log, and so you'll see here there's two cars. What these two cars are. One is, this is an old log. One is what our car did originally in this log. And one is what the car will now do with the new diff that the engineer is testing here. And so you can see this example, basically, we just thought that in the original, the car was getting a little too close to these bikes, especially this last bike who kind of went across surprisingly. Like it comes from way over here and kind of jumped over here. And we just we felt like we got a little bit too close to where that bike was going across. So what we do is replay the log, and so then the engineer can see, okay, did I fix the problem? Now, what actually happens now? We've got a whole regression set of these scenarios, right? So what actually happens is the engineer fixes this one and then runs against the regression set and finds half a dozen other things they just broke, right? And then the cycle continues, right? Until they can actually correct everything, including making the improvement they were just doing. Okay, what else? The issue with replaying previous logs is it's good for small differences, but the actors just do the same thing they did before in the log, right? If you make a big difference in your behavior, they will also make changes in their behavior, and that's not recorded in the log, right? So to test more thoroughly, you need a simulation from the ground up. There's not much in this one, but we also do these ground up simulations for testing. Now, if all goes well, then you go out for track testing. And so what you'll see here, of course, on the roads, our cars have safety drivers on them. And in fact, even on the track, virtually always the cars have safety drivers on them. But it is a closed track, so we don't have to have the safety drivers. We could pull them out. And so in this video, all the cars you're seeing in this video have no one at the wheel. These are just driving around on their own. And so what you're going to be able to see is, just the different sort of challenges and stuff that we can give the cars when they're on the tracks like this. In this case, they're providing their own challenges by all of them being out there at the same time. And so here, this is one of our pedestrians, and you could see that you could probably see the guy in the background was actually just pulling him out on a wire. So we have pedestrians and bikes, all kinds of stuff now. They're all radio controlled now. So you just go out there and you kind of drive them around and mess with the cars however you want. It's a lot of fun. Okay, so what happens then? Okay, if it's okay on the track, it passes all the gauntlet of challenges that are on the track. Then it goes out for a small testing deployment, and then eventually to the whole fleet. And if things go well on the whole fleet, hopefully you have something like this. I'm going to show you a bike example just because this is one of the hard ones, right? We're here following this bus, and then there's this bike. Should I pass it? Maybe. Oh, no, back off. They're in front of us. Okay, maybe now I can pass it. Oh, maybe not. Maybe now I can pass it. Okay, now I can pass it, right? So even for human drivers, we've all done this, right? It's impossible to figure out when you should pass the bike, right? And so this is one of the challenges that the cars have to figure out and do well here. This really combines all of the detection and especially the prediction of where the bike's going to go in order to get these right. Okay. So that's a little bit about our software development process. What I want to do now is jump over and just talk a little bit about the product and sort of where we are with this. Those of you in Pittsburgh or people that were reading the news know that in September of 2016, Uber launched its self-driving product here in Pittsburgh, right? And so still, the safety drivers are still in the car, right? They're still there to take over for anything that the car hasn't figured out yet. But what it meant was, once this launched in Pittsburgh, when you called for an Uber, if you were lucky, you might see this on your phone, right? And so if you click OK to this, you'll get one of these self-driving Ubers. Otherwise, if you don't want to ride it, they'll send you a regular person to pick you up. And so when you get in the car, this is what you see. So you can see that's the safety driver. They're still sitting there. That screen at the front is what the safety driver can check on. And in fact, there's a co-pilot on the other side that's got a whole laptop monitoring everything. But you're the rider, so this is what you get to see here. And what it shows you is, here's the car, and it shows you all the LiDAR, and it shows you everything the car's seeing, how things are detected, and so you can see what the car is seeing. And so there's something very interesting about this from a user experience, and because one of the questions we get is about user adoption. Are people really going to be willing to get in one of these cars? And we found out something interesting when we did this, which is when they get one of these cars for the first time, it's exactly like any of us would be. It's like, oh my gosh, I can't believe it. I'm in a self-driving car, and they're immediately asking the guys in the front seat, hey, what's this? Why is this on the screen? Why is that orange? What's going on? Are you going to turn there? Does it see that pedestrian? Just going nuts, right? Like literally on the edge of their seats. And then what happens is they see this. It says, capture your moment in a self-driving Uber. It's a selfie button. So what it does is you hit the button, it takes a picture of you, screen grabs this screen and puts your picture over the top of it and sends it to you. And as soon as they find that and get that picture, they're so busy texting all their friends, hey, look at me, that they've already forgotten that they're riding in a self-driving car. And so, so for me, that was like a good indication for what user adoption is going to be like these. There will be the usual, early adopter, late adopter curve, but that first part is going to go pretty fast, I think. Okay, just jumping ahead, I'll skip that. I've kind of shown you most of that. 6 months later in Phoenix, we launched the same thing there. And then scrolling farther ahead, most of you read the news. A little over a year ago, right, we had the bad incident in Phoenix. And so when that happened, we basically pulled back the testing quite a bit, right? We pulled the cars back off the road. We reviewed all the safety top to bottom, made lots of changes. And then last December, we put the cars back on the road, but this time just here in Pittsburgh, many fewer cars on the road, sort of a smaller, more focused effort on testing. So just sort of scrolling that whole thing ahead. All right, so I want to just comment a little bit, moving forward, when these things are ready to go, when they're out widespread, what are the other impacts? I talked about safety already. But there's many other things, right? So there's something I find interesting. So the US government analyzes how much time we spend stuck in traffic jams. They use this to understand where it would be worthwhile to build more roads in order of saving us time to not be stuck in traffic jams. And they came up with 42 hours per year on average. But the reality is, it doesn't matter whether I'm stuck in a traffic jam or not, I am wasting time when I'm driving, right? It's actually 7 work weeks of time that we spend driving our cars on average. And so if we didn't have to drive, I mean, think about it. If you got 7 work weeks back this year, what would you do with it, right? There's so many things. Some of us would work harder. Some of us would spend more time on the beach. Some of us would learn a new skill, right? All kinds of things. But just think about that. If you got 7 work weeks back every year, what would you do with them? Another thing is space, right? There are 1 billion cars in the world. Most of us own a car. And what's our car doing right now? Nothing. It's just taking up space, right? In the US, in some cities, up to 20% of the land is just devoted to parking. If these cars are not going to sit there and do nothing all day, we can get back that space. And we can figure out what else we want to do. We have lots of options here. And one of the really cool things is, one of the cool impact factors that are coming along with this is that financial ownership of cars isn't going to make sense anymore. So right now, if you just do the math and said, hey, I'm not going to own a car, I'm just going to take Uber everywhere, Uber would love that. But financially, for most people, it doesn't quite work. It's close, but it doesn't quite work. But 80% of that fare goes to the driver, right? So now you have, some of that's capital costs, which you still have to pay. But there's a big opportunity to reduce that fare. And once that happens, most people don't need to own cars anymore. So this makes the whole market much more liquid. We don't need all this parking infrastructure. We can do, whatever we want. This is our chance right now. Figure out what we want to do with the extra space. And the other big interesting thing is that everybody loves public transit. It's the right thing to do for all of us, right? But many cities struggle to make their public transit financially viable. And so what this does is, again, give us a chance to say, hey, let's just do a reboot. What is the best public transit system given this change in how transportation has worked? So it's very exciting just to have this opportunity to just re-ask those questions of what our cities should look like. Most of you are aware of this, right? It's not only people that get transported. There's food, there's long haul freight. All these things Uber and many other companies are working on as well. And self-driving vehicles will change these things quite a bit as well. And so just to sort of summarize that section, this all works amazingly well, right? So just doing what I described to you, we gave 50,000 trips, mostly in Pittsburgh and Phoenix, to people that just called for an Uber and got that message on their phone. In those trips and in our own testing, we've done 3 million miles driven autonomously. The magnitude of it is quite impressive, actually. Okay, so what I want to do now is, again, switch gears and just get to, okay, great. I said amazing progress. Why is my Uber not self-driving when I call it to go back to the airport, right? What's left to do? So what's left to do? The first thing, we can't really pull the driver out until we've solved the long tail of rare events, right? And so currently, this is an extremely engineer-intensive effort. Again, going back to those box diagrams I showed you, it's a lot of engineers and millions of lines of code behind all that. It's a lot of effort to fix every one of those doing that process I just described to you. Similarly, we need to scale this. For it to be commercially viable, it's not going to be enough to work in one small area, right? We have to go across all of our cities. I can tell you these cars aren't ready for Mumbai. They're a long way. This also, very engineer intensive effort. Every time you want to go to a new part of the city, go to a new city, a lot of work left to be done here. And then finally, we need something to validate and verify the performance of AI in safety critical systems. So there's an interesting fact here, which is there's a ton of systems out there that use AI. We experience them every day online. There's also a ton of safety critical systems out there. We drive, we take planes, we rely on the power grids, all kinds of safety critical things. Virtually all systems are either not safety critical or not AI, right? Those two are two different worlds, right? And so there's some work left to do in how we're going to do these for AI systems. So how do we get there? First thing is, this is a machine learning approach. I'm going to tell you a little bit more about Bayesian optimization if we have enough. I think we'll have enough time for me to tell you about this. We want to do resource allocation for testing. So right now, I described what the engineer has to do when they want to land a diff, right? They go through the logs and start replaying things. What do we really want to do? What we really want to do is every single diff for any reason whatsoever, we want to test it on all 3 million miles that we've got logged there and make absolutely sure that every one of those didn't break anything. Computationally, we can't do it, right? The computation just doesn't exist to do that. But what we can do is use machine learning to do a smart allocation of our testing effort onto our diffs to try to be as efficient as possible about testing code. So that's one thing. The other thing is, I told you that Uber abandoned that black box system because they couldn't understand it. But they now have a system that's going to struggle, in my opinion, when it comes time to scale up commercially because of the size of the engineering team you need to support it. And so I think we're going to have to come back and develop some AI-centered architectures closer to that imitation learning system, closer also to reinforcement learning. I'll make some comments about reinforcement learning at the end. I believe that ultimately, commercially, those will be the successful systems. And so we're going to have to get back to that one. Finally, and this is one, I'm not going to say much more about this one. This is the most challenging one of all in some regards. We're going to have to embrace the fact that we are going to have AI-based safety critical systems. And again, my opinion, the kinds of formal analysis that we've done to prove the safety of systems in the past, we should work to extend that as far as we can into AI and machine learning based systems, but it's not going to get the whole way, right? It's just not going to be possible. So, let me give you one example. So if you look at airliners, right, those are heavily analyzed formally, right? And they largely don't use any AI. And so we understand those. So two interesting observations I have about that. One is we can do the thought experiment. A lot of you flew here. We all fly all the time. Why are you willing to get on that plane? Are you crazy? Get in a metal tube with explosions and fires blasting out of the back of it? It's nuts, right? We're in a weird subset of the population that could actually understand that formal analysis that's done to show that plane is safe. But actually, that's not why I get on the plane. I get on the plane because I fly quite a bit, and for the most part, not too much goes wrong, right? That's really the only reason I get on the plane. So one observation. The other observation is we found out the hard way recently with the 737 MAX that even all that formal analysis, that's not perfect either, right? And so as we get to more of these safety critical systems, we are going to have to develop more and more V&V techniques that are statistical in nature, that are based on a large amount of testing, understanding the probabilities of it, and helping us move forward in that sense. So I'm not going to say any more about that because that's not an active area of my research. I know you guys heard from Phil Koopman earlier, and he's got a little bit different perspective on this. He's more in the camp of let's take the formal analysis and push it as far as we can. So if there are questions afterward, I'd be happy to talk more about this topic, but I'm actually not going to say any more right now in this talk because it's not my active area of research. So what I'm going to do instead is I'm going to show you a little bit more about just what some of these methods mean. And so, sorry, I know you should put all the technical stuff at the beginning of the talk when people are still paying attention, but I'm gonna show you a few graphs and equations because I just want to show you what does this mean, active optimization in an expensive black box system. And so here's the picture. This 1D function, inputs, outputs. Here's this function. It's completely unknown to us. What we would like to find out is where is the max of this function. So think about this is an algorithm running in your car, and this is like a parameter of it. Maybe this is the detection threshold for pedestrians or something. And this y-axis is the performance of this system. So this is how well it performs on all these logs, right? And so we want to find what's the setting of this parameter that will get the maximum output here. Now the only way we can search for that parameter, the only way we can learn about this function is we can ask for experiments and say, all right, run an experiment here and report the result to me. Except that this will be a very expensive experiment. Again, I gave you the example, right? If it literally means run your diff on 3 million miles, you're going to burn a lot of cycles just doing that one test, right? So the whole problem of optimizing this comes down to, can you efficiently choose where to do these tests so that you can optimize the system? And so this happens all the time. AI folks use this all the time because they have to tune the parameters of their learning models, so it's very common for them. For the rest of us, the more common applications are if you're tuning a real physical system that you're gonna have to run a physical experiment, maybe it's a car, maybe it's something else. These are expensive, right? You can't afford many tests. This would go under to a statistician. This would be design of experiments, right? The other thing that's increasingly happened is that algorithms are actually tested via expensive simulations. And so what you're really doing when you design experiments is you're allocating compute resources. And so this happens for any of these things, fitting models, computing, optimizing the performance of your compute stack, any other kinds of controllers you have. So how does this work? Okay, great. So there's the problem. Here's this unknown function. What is the algorithm? So here's the algorithm. What we do is say these are the experiments we've run. We fit one of those regression models I was telling you about for supervised learning. We fit the model to it, but we use a certain kind of model that gives us good confidence intervals. So for every point here, we have a measure of our uncertainty about the performance of that area. And so what we can do now is we can say, let's make an acquisition function. And the acquisition function will tell us where is the most valuable place to take another experiment. So if we take the upper confidence bound of our estimate and we choose our experiment at the top of the upper confidence bound, what does that mean? That confidence bound is high. It means two things together. One is we think the function's actually pretty good there, so that's a good place to check. But the fact that the confidence bound is high means also we have uncertainty there. So if we do the experiment there, we'll actually learn something. It's not that we're just checking something we already know the answer to. So that's why you would want to do that. So the way the algorithm works is you fit your model, you define this acquisition function, which is the top of this confidence interval. Then you maximize your acquisition function. Then you do that experiment there and you repeat. So let me show you just in cartoons what that looks like, right? So unknown function, no data, right? So our confidence bound is just, you know, it's just flat. We don't know what's there. So our acquisition function is just flat. So all experiments are the same. All right, let's just take an experiment in the middle. So we do that. We collect this data point. Now the upper confidence bound looks like this. Now the acquisition function looks like this. So now where's the optimal of this? Well, it could be this side or that side, so we just pick one. So, okay, now we'll do that experiment. Now the acquisition function changes. Now the maximum's on the other side. Take that experiment, function changes, and we continue like that. And so what happens is, by the end, just following that procedure, the right thing has happened. We've sort of checked out different areas of this function, but we burned most of our effort near the peaks, near the most promising points. So it's very efficient. Okay. There are many variations on this algorithm for active optimization, but that's one of the common ones, so that gives you the idea. Okay, so professor likes to stand up next to 1D graphs and draw them on the screen, right? It's easy to talk about, but can you do anything real with this, right? Ultimately, real systems have many more than one parameter. They're much more complicated than that. So I promised you a snake robot. I'm going to show you a snake robot now. So this is a snake robot. This is from my colleague, Howie Chosit. His lab, they design and build these things. So here it is. It's got 16 joints. And it acts just like a snake, right? It sidewinds, it slithers around, it can even swim, does all kinds of things. But as a system, it's impossible to write controllers for this thing, right? Because all the dynamics, all the kinematics, everything's nonlinear, and most of the locomotion is governed by friction, which is basically impossible to model well. So how are you going to figure out how to control this thing? Well, the way we're going to do it is we're going to use exactly the algorithm I just showed you. And what we're going to do is give the parameters of some controller to the snake, and we're going to run it and see what the snake did, and that's its score, and then it's going to learn how to improve that. So just to give you a couple of simple examples, this was the best we could do with a human trying to write a controller for sidewinding, so you can see it kind of does this. After just 40 trials, it's able to go much faster. This is a human attempt at climbing this ramp. And the fun thing about this video is, I don't know if you'll be able to see, yeah, I actually have it looping. It's an extremely short video because this just happens all day. That's the best the human can do. And so, but after just 40 trials, what the snake has learned how to do, you'll see it kind of twists a little bit. So every so often it kind of twists itself straight, and it prevents itself from falling over at the wrong time. So it's figured out how to control, how to crawl up this thing. Here's another example. This is maybe the hardest one. So what is this snake for? The snake's meant to, it's disaster recovery kind of stuff, right? There's an earthquake, building collapses, somebody's got to crawl through the rubble and find the survivors, right? The snake. So what does it commonly find? It commonly finds obstacles. It needs to figure out how to get itself over the obstacle. We didn't know how to do this. We couldn't write a controller for this. We actually did something fun. We set it up as a puzzle at the museum. And so the way this works is, here's the snake, here's the obstacle it's trying to get over. So this is a master-slave setup, right? So what happens is, you bend this joint on this snake, and this snake will bend its joint at that place. So you show up and you try to figure out how to get this snake to maneuver over the obstacle, right? And so we set it there for the kids, and you can see how the kids love it. But it turns out the 30-year-old and older kids also like it a lot. This is my sister, and this is the curator for the museum. So it was very popular. And so, but what we found was that this size obstacle was very challenging. Even for this, even sitting there all day, the success rate was about 1 in 10. Only a few people got over the obstacle at all, and with lots of complicated machinations. And so, but we took all that data, all the ones that worked, and sort of compressed it into a parameterized function that we could optimize with a few parameters like that one. And so we did something else. Maybe I should skip this. What we do is, in addition to this 1D, in addition to the actions, we add to the model a context. This is how tall the obstacle is it's trying to get over. So you'll see what that means in a minute. Whoops, I just went over here. So having initialized this snake now, we're like, okay, now we're ready. Let's climb some real obstacles. And so what you're seeing is the blooper reel. So this is sped up 10 times, but this is the snake doing the algorithm I just described to you, right? It chooses an experiment, and then it executes that controller, and then it gets feedback, hey, did you get over the obstacle or not? And then it chooses another experiment. And so what you're seeing is what we discovered is directly giving it a tall obstacle, it just wasn't able to learn. It wasn't able to figure anything out. And so what we did is went to a small obstacle, the one that was in the museum, so we could kind of initialize it with some of those that it worked, and then let it try experiments. And as it gets good at one height of the obstacle, we just keep bumping the obstacle up. Now, what you're going to see is that as it gets higher and the low obstacle, it's able to just kind of just hop over like that. It's not too hard. As it gets to the higher obstacle, it turns out the only way to get over that thing is to kind of curl itself backwards over the obstacle. It sort of figured out, for those of you that remember this, it sort of figured out the Fosbury flop on its own. And so that's a cool thing about the algorithm. And again, so here you can see this is what it looks like in real time doing this obstacle. That's how it goes over there. So it curls backwards that way. What's cool about this is that, you know, we had the engineers that built this snake. They're the ones that came up with all the basic locomotion and stuff. They couldn't write a controller to get over that initial 4-inch high obstacle. But just with about a day, really less than a day of learning, it was able to learn for itself how to get over an obstacle that's much higher than that. So it's pretty cool that it's really solving problems that we didn't have any other way to solve these problems. Okay, so for those of you that are interested in that particular algorithm, that particular active optimization algorithm, we have an open source repository called Dragonfly that pulls together all the work of one of my students who did a lot of these. So those snake examples, those are now like 5 years old now, and they're mostly very low dimensional problems. Most low dimensional in this case means sort of 3 to 6 variables, that kind of thing. Most real problems you would ultimately like to do more variables than that. So Sammy's dissertation, which he just defended last fall, was all about how you increase the dimensionality and still make it work effectively. So this is all in this open source project. Okay. I am mostly out of time, and I would almost rather take questions than spend time on this. So what I'm going to do is just blur by a couple of quick slides and let you know what we're up to. So I mentioned reinforcement learning and getting back to imitation learning to build this controller. And so that's one of the things we're working on now. So this is going beyond just the supervised learning algorithm I told you, where you get a single input and then you make a prediction about it. This now says I'm a system acting in the world and I need to choose sequences of actions that could have long range effects. How should I do that? And that's the area of reinforcement learning. Those of you that watch the news may have seen the computer that beat the world Go champion, and so that's a reinforcement learning algorithm. And I want to just give you a little bit of insight into how that algorithm works, just in case you're not familiar with it. So tic-tac-toe, how do we all learn tic-tac-toe when we're a kid, right? We build the game tree, right? We say, well, the board's empty. Okay, if I put the X in the middle, then my opponent could put an O there, could put an O there, and in fact it goes wider than that. And if they do that, well, I could do this. And you build this whole tree out to the end, and you find all the wins, the draws, the losses, and then you work backwards to the one that actually works for you, right? So as a kid, you can't quite build the whole tree to the end in your head, but a computer can, right? So it just builds the whole tree, solves the optimal thing. Great. Go has an estimated 10 to the 170th states. So you're not going to build that tree. you've got to find efficient ways to go through and build that tree. And so that's what reinforcement learning is, right? Driving all acting in the world is like Go. You've got to make actions, but there are going to be some longer term consequences. You have to think about what the world might do to you as a result of those actions and how you might respond to the world. It's the same thing, right? And so what AlphaGo did, and how all these deep reinforcement learning algorithms work now, is they use this deep learning network to learn a model of how good each state is. So like if this is what the board looks like, is that good or bad? And here's my current policy. If this is what the board looks like, here's what I'm going to do. And so it has algorithms to play and then improve both of those estimates at the same time. And so my apologies for that being too brief for you to get the idea, but there's lots of good work on reinforcement learning as well as good tutorials if you want to hear more about those. We're actually working, so this is now in simulation, but this is a car learning to do stop signs through the use of reinforcement learning. So these are things we're working on now. And I'm going to stop because I would rather take questions than go through all this. My summary is just this. We're developing ever more complex engineered systems, and they've reached a level of complexity where it's not going to happen by just programming them. They are going to be fundamentally machine learning and AI systems. And we need to adapt both our methods for developing those kinds of systems and our testing and validation procedures to handle these kinds of systems. So with that, I'll just stop and take any questions you guys might have.
How does it handle snow?
It's a great question. Snow causes all kinds of problems. Okay, so there's the obvious one. You lose traction in the snow. Although for the most part, we're going to rely on the traction control that already exists in cars. So that's one. Another one is when it's actually snowing, it's not great for the LiDAR and to a lesser extent the camera, because you get pings off the snowflakes and they obscure what you're actually trying to see. And finally, if it's been snowing a lot and there's snowbanks stacked up all over the place, it makes your map not match what you're seeing in the road in real time. So all kinds of problems with snow. And the short answer to that is it's not an accident that all the car companies are testing in places like Phoenix. And so even in Pittsburgh, we do okay in the snow, but when it gets super cold and snowy in Pittsburgh, we just don't send the cars out that day.
I've heard a vision of these vehicles communicating with each other, and further that someday that freeways would be restricted to only autonomous vehicles. And I wonder how that changes the engineering problem or the architecture, that these vehicles communicate, and further, you only have vehicles around you. Now, obviously, the moose, the kangaroo problem still exists.
Yeah.
But it changes your problem a lot.
Yeah. So in the future, this is a little bit sad. It's sad in the following way, because once all the vehicles are talking to each other and once the infrastructure is talking to all the vehicles, this whole entire problem gets way, way easier, right? Even the little things like, why should we look at that traffic light and try to figure out what color it is when the sun's shining on it? The traffic light can just tell us what color it is, right? Like every little, everything is going to get way easier. But the annoying thing is, all that infrastructure depends on the government to put the infrastructure in there. All the communication basically depends on standards to be developed by committees across all the car makers and stuff for all that. And so basically, if we want to get there first and fast, we can't really wait for all that stuff to happen. So we already know we're building a system that's solving a way harder problem than what will ultimately be the problem. I want to make one comment. Just this, I find this funny. You said highways that are restricted and only self-driving vehicles can be on there. I think it's funny because if you I don't know whether you would call this utopian or dystopian, but if you think about it, we all used to get around on horses, right? And now horses aren't allowed on many of the roads. And if you want to ride horses, you go to a ranch somewhere that's set up just so you can ride. So now if you think about a self-driving car, once these things work and you're the passenger, what do you really want? What you want is, hey, you know what you're doing, and your sensors are way better than anything I could ever do. Go faster. Get everybody, go faster, right? And so you can imagine roads that all the traffic is moving so fast that humans are no longer capable of riding on these. And we all can go to ranches if we want to drive a vehicle and reminisce about what that was like. So, yeah.
I love the closed course because for the testing, because your integration testing essentially is physical.
Right.
My question was in simulation. On the other hand, do you do anything along the lines of adversarial methods to help improve the training process?
Yeah, so we don't at the moment have like those kinds of really integrated AI-based adversarial algorithms, but there is research going on in the broader community in that area, and I think that's going to be critical to really solving these problems because the rare events are so rare that you need algorithms to go find them for you. Yeah.
What's your experience in driving on country roads with no markings?
Oh, it depends. Again, two answers, one for each system, right? The what we call the engineered system. It's not really a problem because the lanes are marked in the map. So it doesn't really matter if you're localizing off that oak tree or that barn or whatever else. Once the lanes are in the map, you know exactly where the road is. Now for the imitation learning system, that one's actually surprisingly robust for that kind of thing. It uses the lines, but when they're not there, it still figures it out from the broader context. And we found this out when one of our managers who came for sort of a first ride in this car, right around the time I took that video from the stop sign. We drove around a few blocks and did some stop signs and some other things. And he said, okay, this is boring. I know you trained on this part of the road. Take me somewhere you haven't trained on. And so he pointed over to Railroad Street that was over by the building, which is kind of a crumbling road that's next to the railroad tracks. And there's no lines and it just falls off. And so we had never even given it any data with roads with no lines, but actually it drove down the road fine. There was enough context from other things. And so especially if you train on that kind of data, it's pretty easy. And in fact, there are some other folks that, if you look at the NVIDIA's self-driving car, and more recently there's a company in the UK called Waze that did one that was more like on a country road. If you actually train on those, it's pretty easy. It's not an issue. Yeah.
Hi, thank you for the talk. So you mentioned for the long tail problem, a lot of very intensive engineering work is going on there. So my question is, yeah, it's a very long tail, and even though a lot of engineer work going on there, how we can set up the criteria that says, okay, we hit some milestone and we're good, we're safe to go on the road. So how to define that criteria?
Yeah. So this gets to the how you do the safety critical stuff, how you do the testing for it. I can give you you heard Phil give you one answer to that question from earlier. I can give you my answer. My answer is, as you've run enough in your logs that you think it solves all the common problems, you need to do it more statistical. So you need to again use these sort of resource allocation algorithms to have those releases spend more time on the road, log more miles on that, and ultimately answer the statistical question that says I've spent this many miles on the road, I've spent this many miles replaying my old logs, I've spent this many miles in simulation on this particular release that looks pretty good. In aggregate, that has reached my confidence threshold. Now we know that it's going to be extremely hard to verify that they're perfect, right? There will still be mistakes, but the main thing is we want it to be better than a human driver would be, and at that point it's a win to put it out there. There's a big mental shift though, right? Because just like anything else, even if the machine makes less mistakes than the human, it makes different kinds of mistakes than the human. And it's really frustrating when a machine screws up on something that a human would do, obviously, right? Again, getting back to the 737 MAX, right? That is extremely frustrating because any pilot, not a pilot, even me, could have looked at that situation and said, this is nuts, you know, pull up, and yet the machine didn't. And so there's still sort of some ways of thinking to get around, but I think that's ultimately the procedure we'll end up using for these things, you know.
Was the programming language used
It's mostly C++. A lot of the off-board stuff, of course, everybody likes to work in Python now, so a lot of the off-board stuff ends up in Python, but the onboard is mostly C++.
It's